Okay, I think it's work. So welcome again to the poster session. Okay, so the first speaker is David. Are you there, David?
Yes, hello.
Okay, hello. Please, you have 7 minutes and there are 3 minutes for question, okay? I will stop you if you take too much time, okay?
Okay, so you want me just to describe the poster or you want me to run a small presentation?
Describe the poster, yes.
Okay.
So, I mean, you can present and discuss your poster as you want. Just Alejandra will help you in moving the poster. So you have just to say if you want to go up or down or whatever, or to focus on a particular part. Okay.
Okay. Thank you. So basically, in the introduction, I describe what is the motivation of this study. So basically, the idea is that we want to study the possibility of dark matter interacting with the magnetic field of the sun. And if dark matter interacts, it's possible that it decays and creates the so-called cosmic ray ensembles. That is a big shower where most of the particles are correlated either in space or time. And this has many motivations. For instance, to try to understand the effect of the limit of Greisen-Sapsen-Kosmin that is related to the interaction of high energy particles with a cosmic microwave background. And so if you go a bit down in the poster, so we consider some equations for the interaction of these dark matter particles with the sun, and given these interactions, we could study some rates of production of these ensembles. And basically, if you go a bit lower in the poster, we have considered two types of configurations for the magnetic field of the sun. One is that is very crude, but it's like the first approximation, that is the dipole field. And the second one, it's a quadrupole moment, magnetic field moment field. As you can see in this figure, you have on the left and on the right, they are a bit different, but qualitatively, the results are similar. That means that the dipole field is not such a bad approximation. It's just that it's not that as accurate as the quadrupole. And now I would like to show you on the right side the results. So basically you have see here the size of a footprint. That's what is detected on the Earth. So once the dark matter particle decays and creates a very extreme showers, it can be distributed in very large areas. And what you see here is a footprint size in kilometers. That means basically, as you can see, is huge. With the dependence of the impact parameter in solar radius. This is basically the distance from the sun to some point where the shower is created in the vicinity of the sun. And if you go a bit down, you will see the typical shower footprint. This is derived of the performing simulations for the propagation of the shower on the top of the atmosphere down to the ground. So this is how we expect to see it on the ground. And if you see, go to the last figure down there, you will see that in the case of a standard shower, what you see is basically just a circular or rather uniform distribution of the particles. But in the case of these cosmic ray ensembles that are correlated, what you see is this kind of elliptical shapes follow or together with this elongated line. We call them galaxy-like footprints. And the idea is to try to detect these showers. And for that, there are several proposals. One of them is to use the already running observatories like OJER in Argentina or in the north, the telescope array. But since these showers are really extreme, we will also have discussed the possibility of using smartphones. So in the framework of the CREDO project, There's an app that you can download and you can try to help us to detect these cosmic ray showers all over the earth by running the app in the smartphone, for instance, when you sleep, when with a camera cover or things like that. So basically, this is what I wanted to share with you. Thank you very much. If you have any questions, please go on.
Thank you, David. Is there any question for David?
I may have a question indeed for David. Well, first, I think it's quite interesting, to be honest. This is a very nice work, so congratulations. I was wondering about the energy scale that you are mostly interested in. You mentioned the Pierre Auger Observatory, but will this also be happening at lower energies, or TB energies maybe, or I don't know? Can you maybe comment a bit more on the energy of these events?
Yes, thank you very much for the questions. We are looking for very high energies because in order to produce these very extended footprints, we need energies of the order of electron volts. So we need either very heavy dark matter particles, or we need to have some other kind of very energetic process where, for instance, a photon will split or something like this. But we really need extreme energies, so ultra high energy photons.
Okay, thank you.
Any more questions? If not, we can maybe go to the next poster that is by Pooja. I hope
Yeah.
Hello. Hi. Okay, please, when you want.
Okay. So the topic of my today's poster is the multi-wavelength analysis of low surface brightness galaxy in order to study the possible dark matter signature. This work is recently published in Eminares, and the motivation for our study is that low surface brightness galaxy, if you read the abstract, then you can have an idea that what is the motivation of this poster. Low surface brightness galaxy is considered as a very rich in dark matter content, and for our studies we have chosen 4 low surface brightness galaxy and try to estimate the possible gamma and radio emission that we might expect from the dark matter annihilation. For gamma ray part, we have taken the data from the Fermi-Large telescope, and for the radio analysis part, we have used the sky survey data by the VLA. And besides, we have also tried to check whether with some future upcoming telescope, we can say anything regarding the dark matter signal that we might expect from the low surface brightness galaxy. If we can go below to the poster and maybe the analysis methods, where we have given that which energy range I have chosen for our study. Like for gamma ray part, we have chosen the between the energy range 500 MeV to 300 GeV, and use the toolkit DMFIT toolkit in order to estimate the possible dark matter annihilation or possible dark matter signature that we can expect from the gamma ray emission. And for radio emission, we have used the publicly accessible RxDMFIT code, which this code is used to solve the diffusion equation or transport equation of the charged particles. And if you can go to the right section of this part, poster, yeah, just go ahead. Yeah. So here I have also explained the formulation part. I'll briefly explain about the formulation part. The first equation is the expression for the differential photon flux that we can extract from the dark matter, or we have said it as a WIMP planning pair annihilation. This factor is this term is the factor of 2 factors. One is the particle physics factor, which depends on the particle prospect of the dark matter annihilation channels and its mass or any other properties. And there is another factor, which is the termed as astrophysical J factor, which depends on the shape or distribution of the dark matter. So this first from equation 1, 2, 3, this equation is related to the gamma ray annihilation part, and where if we come check the equation 4, this equation is needed to estimate the possible radio emission. I mean, not necessarily radio, possible X-ray or radio emission that we can expect from the charged particles, which can generated from the WIMP annihilation. For our study, we are basically try to consider that the gamma ray and the charged particles, which can generated from the annihilation, which can generated as the end product of the annihilation channel. And in the presence, in case of the charged particle, relativistic charged particle, in the presence of the magnetic field, they can generate the radio emission through synchrotron emission process. And for our study, we are interested to study that whether we can obtain any synchrotron or radio emission from the LSB galaxy. So in this diffusion equation, you can see there is a QE term which defines the source term for the dark matter annihilation. And if you can go below to this section where I have it, yeah. So first we have tried to check what from the gamma ray study, from the gamma ray data. First we have tried to check what limit we can obtain from the low surface brightness galaxy. So here I want to mention that in case of the low surface brightness galaxy, there is one disadvantage. I mean, they
I cannot hear. I'm the only one.
No, me neither.
Yeah, hello, can you hear me? Sorry, there is some network failure from my side. Hello?
Hello, now I can hear you. Okay.
Sorry, there is some network issue. Yeah, sorry. So first, in the if you see two images under the section of the A, here we have the first one, the left one, where we have tried to predict the possible gamma ray limits that we can obtain from the Fermi-Lab data. But in case of the low surface brightness galaxy, which resides at the megaparsec order, so if for that case we could not expect to obtain very strong limits from the gamma ray data. So we have again, so from here you can see that we have compared the limits that we can obtain from the LSB with the limits thermal Rayleigh cross sections, and also the limit that we can expect from the dwarf spheroidal galaxy. And we can see that because of their distance, the limits that we can obtain from the gamma ray data is at least 2 orders weaker than the limits that we than the thermal Rayleigh cross section. So we have also tried to predict what could be the possible limit cross section time velocity limits that we can expect from the radio data, and also make a comparison between the radio and gamma ray. And from our study, we have shown that because of the large uncertainty associated with the both data, we could not say that gamma radio could provide a better limit compared to the gamma ray, but from the overlapping region, we can see that radio could have a chance to provide a better limit compared to the gamma ray. So from here, we can say that in case of the low surface brightness galaxy, radio could be the one of the better probe than the gamma ray in order to estimate the possible dark matter signature from LSB galaxies. If you go below, yeah,
You are almost over time, so just take your time to finish it, okay?
Yeah. I have also shown that how the spectral distribution, how can the spectral distribution vary with the astrophysical parameter like magnetic field or diffusion constant. And we have shown that for the synchrotron emission, it is strongly depend on the magnetic field, whereas both synchrotron and inverse Compton emission, I mean both radio and X-ray emission, both are strongly depend on the diffusion coefficient. And if you go further below to this, yeah, as we can see that from the radio or gamma data, we could not expect to obtain very strong limits for LSB galaxies. So we have also tried to check whether with the future telescope like SK or with the CT, we can expect to obtain or expect to detect any emission from the location of the LSB. So we have compared the possible radio flux with the SK sensitivity curve, and we have also compared the gamma ray diffusion flux with the CTA sensitivity curve. And from our plot, we can say at least that, okay, in future, we can expect to detect any positive emission with the help of the CTA and the SK. So, yeah, thank you. There is the conclusion.
Thank you, Pusha. Any question? Actually, I have a question for you, and I don't know if I lost it in some moment, or do you have any just one target between your LSB, or you have more target?
No, we have chosen 4 LSB galaxies, and here we have shown the result for one LSB galaxy. But if you check the combined limits, which is obtained from the limits for the 4 LSB galaxies.
Okay, and I would also like to ask you the range of masses of these galaxies and their distances. Sorry.
Yeah,
The farther one, yes, the farther.
I mean, the distance is around the megaparsec order. We have tried to choose those LSB galaxies which are lower than the 15 megaparsec. Otherwise, the J factor or astrophysical factor will be further reduced, and the mass to light ratio would be lie around 100 to 1000 order. I could not remember the exact number, but it will be lie between 100 to 1000.
Okay, thank you. Any other question?
I may have one indeed. I was wondering about the density profile that you assume for these objects, because I know that these masses are tricky in the sense that they, some observations point to cores.
Yes.
So can you comment on the profile that you use?
Yeah. I mean, yes, LSB for a low surface brightness galaxy, there is some studies that the core profile could be the better one. But for our studies, we have chosen the Caspi profile, because the 4 LSB galaxies like UGC 12632, UGC 3371, from the we have checked that the Caspi profile could also provide a better perfect fit to the rotational curve to those LSB galaxies. So for our studies, we have chosen the Caspi profile. But in our paper, if you can go through our paper, you can check. We have also shown a comparison between the core and Caspi profile and tried to comment something on that. But the result is also based on the Caspi profile.
Okay, thank you.
Any further comments? Maybe we have time for one more comment or question.
There's a question in the chat by Claudio. He
Okay.
says, what should you consider for your background?
Yeah, background. I mean, in case of the data analysis, if we consider the data analysis, I mean, if you consider the gamma analysis part, we have to consider there is we have to consider the galactic or extragalactic diffusion component and any other background nearby sources. All this component we have to consider about in order to run our analysis. Yeah, are you asking about that, or you want to ask something in detail?
Did you check if there is a proper radio emission from these galaxies in the radio?
No, they does not show any strong emission from the galaxy. That's why we have chosen this 4 LSB galaxy, because they does not show any strong emission from the
Okay. Okay, thank you. I think we can switch to the next speaker, that is Bastian.
Okay, do you hear me?
Yes, we can.
Okay, thank you, especially to the organizers of this activity. And well, my name is Bastian Diaz-Saez. I am from Chile. I did this work in collaboration with these people that appear in the title or in the authors. And the title is Fermion Dark Matter in a Pseudoscalar Dark Matter Portal. So basically, what we did was we studied a simple extension to the standard model in which we consider 2 new fields, a Dirac fermion and a real pseudoscalar. And when you introduce both fields, it is not necessary in principle to have additional symmetries in order to make them stable. So in that sense, we found in some in some regions of the parameter space that both particles can be stable at the same time. And we study the relic abundance production via freeze-out. And also we impose some constraints on the results. So basically, as you can see, here is the Lagrangian. Very simple. The third term in the right side is the interaction between the 2 singlets, the fermion and the pseudoscalar. And also you can construct at the renormalizable level this potential between the Higgs and the pseudo-scalar. So basically we have 4 new parameters, the 2 masses of the singlets and the G psi and the Higgs portal coupling, which is lambda HS. So we started this work from the freeze-out point of view, in which basically we assumed that in the very beginning, the 2 particles were in thermal equilibrium, and then at some temperature, they decouple and originates what is called the Rayleigh abundance. So in the right side, for instance, we can see that, just to sketch the mass range that we explored, from 10 GeVs to 1 TeV for both particles, and not all the points are allowed in order to have both fields stable. For instance, the green region is not possible because that means that the mass of the pseudoscalar will have masses above twice of the fermion mass. So in that sense, it will decay, the pseudoscalar will decay into 2 fermions. So basically, we explore all the rest of the region, which is not green. So in below, you can see the Feynman diagrams. Can you scroll down a little bit, please? So you have in the last row the typical annihilations that you find in a Higgs portal dark matter model. So the pseudoscalar going to standard model particles and the Higgs boson. And in the first row, we have our new possible interactions, which basically A and B are semi-annihilations, and B and C and D are dark matter conversions that play. So all those diagrams playing some role in the calculation of the Rayleigh density, which we calculated basically, as you know, via Boltzmann equation. And as we have 2 dark matter candidates here, we need 2 Boltzmann equations, which are coupled one to each other. Basically, the lambdas that you see in the equations correspond to the diagrams that you see in the right. So we solved this system, this complicated system, using our own code in Python, but also we cross-checked our results with Micromegas. So in below, can you scroll down, please? So our results are condensed in these plots. Basically, the color plots that you see, the 3 color plots represent the Rayleigh abundance. Well, it's a random scan that we did in the couplings and in the masses of the new particles, and we projected on this plane of masses. And as you can see, the color indicates the Rayleigh abundance, and the left plot is the total Rayleigh abundance. In the middle plot represent the abundance of the fermion, and the last one to the pseudoscalar. So there are some details here that, of course, I'm not going to enter. But basically, after imposing some Rayleigh abundance, the correct Rayleigh abundance measured by Planck, direct detection, and Higgs to invisible, we found that in figure 4 that there are 3 regions allowed by all these constraints, which you can see in the green, orange points. So basically, most of the parameter space is already ruled out, and we also studied we took the points above the region, which is more dense, let's say, and we explored the signals for indirect detection for those points. And in resume, we didn't find any new constraints coming from Fermi-Lat or projections, even projections from CTA, and also from AMS, which are in the figure 4 in the right. So basically, in order to complement that that result, in the last part in the left below, we we contrast our what we found in the differential flags for some of the points that passes all the constraints, relic abundance and direct detection, which are the continuous, the solid lines, the green and blue. You can see that the flags that the model predicts via one channel, that is the semi-annihilation, is some orders of magnitude below the red dashed line, which is what is measured by Fermi-Lat. So basically, that is what we study. It's as I said, a very simple model in which we introduce two singlets, two gauge singlets. No new symmetries were required in order to stabilize them. And we studied the parameters from 10 GeV and up to 1 TeV for both particles, and yeah, we constrained all the parameter space via relic abundance, Higgs to invisible decay, direct and indirect detection. So that's all. Thanks.
Thank you, Bastian. Any question for Bastian?
Seems that everything was very clear.
Okay. Okay, if not, maybe we can switch to the next speaker. Thank you, Bastian, again.
Okay, thanks.
So the next speaker is Rashmi.
Hi. Can you hear me?
Yes, we can.
Okay. So I am Rashmi Har, and I'm a PhD student from the Scuola Superiore Meridionale in Napoli. And I am going to talk about heavy decaying dark matter at future neutrino radio telescopes. So the main goal of this work is to forecast the limits that we can place on the lifetime of heavy decaying dark matter using the future neutrino radio telescopes. In this work, we are going to assume that these dark matter particles can decay into a pair of standard model particles. And we're going to assume also that the minimal decaying dark matter scenario with only two dark matter parameters, the mass and the lifetime of the dark matter. So in the first panel, I show the neutrino the scheme of neutrino generation from dark matter, where we see that as I said, the dark matter particles decay into a pair of standard model particles. In this work, we are going to focus on these three channels, the B, tau, and nu channels. And from these decay products, we will obtain neutrinos that will travel and reach the Earth. And these are the particles that we will measure on the future neutrino radio telescopes. So first, we will use the HDM spectra code in order to produce the neutrino fluxes, well, the neutrino spectra coming from dark matter. And then we will generate these two different contributions, the galactic and extragalactic ones that we can see on this first panel. The galactic one contains the two dark matter parameters for a neutrino flavor alpha, and also the neutrino spectra for that flavor. And the raw DM is the dark matter allo profile. In this case, we choose the Navarro-Frank-White profile. For the extragalactic contribution, we have also the two dark matter parameters, and we can find also rho sub c, that is the critical density of the universe. Omega dark matter is the dark matter density in the universe, and we will also find the redshift, that is Z, and the Hubble parameter, in which we will take into account the latest Planck measurements. So this is the dark matter fluxes that we will obtain. This is the way in which we obtain the dark matter fluxes. So if we move now to the second panel, in which we will see the high energy neutrino flux scenario, we can see that we have shown here three different, for each channel, for a particular benchmark scenario, the flux that we obtain from the dark matter, just to see the shape. That, I mean, in purple we can see the neutrino channel, in orange the tau channel, and in green the B channel, for a particular choice of mass and lifetime of the dark matter, just to depict the shape of the fluxes. And we will see here, we can see here also the latest IceCube's HESE data release, that is the IceCube 7.5 year HESE data as black dots. And we can also see two different astrophysical expected fluxes. I mean, beyond these black dots, we have not measurements. So these are expected fluxes that are in red, we have the cosmogenic fluxes, and in blue, the newborn pulsar fluxes. The cosmogenic neutrino flux is expected it's a guaranteed contribution because it will come from the interaction of the cosmic rays with the CMB photons. But it is uncertain in magnitude, and we will, I mean, in reality, we have a band, but we have chosen the upper limit of this band in order to make our analysis conservative. And for the newborn pulsars case, we have chosen this particular case because it is the highest neutrino flux scenario that we found on the literature. And we also chose the upper limit in order to make our analysis very conservative. And we can also see the different sensitivities of the different neutrino telescopes that we are going to take into account. We have IceCube Gen 2, IceCube Gen 2, RNOG, and two different configurations of GRAND that are 10K and 200K. So if we move now to the third panel, with that fluxes, we can now obtain the different number of events that we expect in the future, because this is a forecast analysis. And we will find that for each mass, we can obtain the number of astrophysical expected events from each source, the cosmogenic one or the newborn pulsars one. And from this number of events, we can obtain the probability of observe a certain number of observed events. And after this, we are going to make another conservative choice, that is that we are going only to constrain signals where the number of events that come from dark matter is higher than the expected observed number of events. And in order to do that, we use the following test statistics, in which we can see that it is 0 for the case in which we have lower number of dark matter events than the number of expected observed events. And we assume that the likelihood is a Poisson one. So with this, we just proceed to see the limits. We show on each column the, can you scroll down a little bit, please? So we can see the different experiment in each column, and the different dark matter decay channel on each row. And on each plot, we show the different constraints that we placed for what we forecast. For each astrophysical scenario, the cosmogenic astrophysical one, the newborn pulsars one, and we also include the case in which we won't see any astrophysical signal, which is a possible case because, as I said, the astrophysical fluxes suffer from high theoretical uncertainties, and we don't know if we are going to even have any astrophysical event. So basically, in the neutrino case, we can see that we have a gray line, which is the existing constraint placed on this channel. And we can see that we have placed for all cases higher constraints. On the B channel, we find that our results are complementary to the ones that exist on the literature. And for the tau channel, we see that we weren't able to find any result before, so we placed new constraints. So basically, to conclude, this can you scroll down just to the conclusion? So, thanks. So these radio neutrino telescopes will be able to detect a dark matter contribution, a decaying dark matter contribution, and in this work we have performed a forecast analysis in order to set conservative bounds on the lifetime of heavy decaying dark matter particles, and in the range of masses of 10 to the 7 and 10 to the 15 GeV. So that's it. Thanks.
Thank you, Rashmi. Any question to Rashmi?
I have a question. How will the observation of neutrinos from pulsars constrain dark matter? Could you say it again?
Well, I mean, on the second panel, I mean, we just took a neutrino. I mean, from an existing plot, we took the newborn pulsars. I mean, the neutrinos that will be generated from the neutrino pulsars, and as you can see, the contribution coming from the newborn pulsar is higher than the cosmogenic one on the second panel, and basically this will lead to lower constraints, because if we have a higher number of expected events, we expect that dark matter would need lower lifetimes in order to produce a visible signal. I don't know if this answers your question.
Thank you.
Any other question or comments? Okay, if not, we can switch to the next speaker.
Okay, thanks.
Sorry, we can switch to the next speaker, that is Isabel.
Yes, can you hear me?
Yes, we can, please.
Okay, nice. Okay, so I'm going to present some results on constraints for indirect dark matter searches. So the idea of this project was to use the high statistical precision data from the AMS-02 experiment to compute constraints on leptophilic dark matter for cosmic ray positrons. And if we look first at figure 1, if you could maybe scroll down a little bit. Yes, no, to the right, please. Yes, thanks. So this is a sketch of the positron flux as measured on Earth. So we have different contributions. So at low energies, we have positrons that come from secondary production. So that's mostly protons, like about 90%. And then 10% from helium that decay or interact and produce positrons. And then as you can see at higher energies, we get a rise in the positron flux. And this was unexpected when it was first discovered. And the two most prominent explanations were a contribution from dark matter or from pulsars. But lately, the dark matter contribution has become disfavored by other constraints and observations, and the pulsars have become more favored. So what we assume here is that this rise in the positron flux comes just from pulsars. And then on top of that, we add, and just to say, so pulsars, they rotate, and some of this energy can be converted to electron-positron pairs. So that's how they produce positrons. Okay, and then on top of that, we add small dark matter contributions from annihilating dark matter. So in this example, the dark matter annihilates into an electron-positron pair, but we also consider other leptonic decays. So I will show you in a bit. But first, just to be a bit more specific about our model, maybe could you scroll down a bit? Or maybe a bit to the left. Yeah, it's okay. Okay, so yeah, perfect. Okay, so to build our model, we use GalProp, which is a cosmic ray propagation code. And we want our model to be flexible, so we leave a lot of free parameters in this model. For example, the diffusion spectrum of the particles in the galaxies, or this galaxy, I mean. Then the injection spectra of protons and helium, and the pulsar distribution in spectrum, for example. Okay, and then we fit this model to the data from AMS for positrons, protons, and helium. And then we get a plot like this in the bottom left. If you could scroll down a bit, please. Yes. So in the left plot, we see the positron flux on Earth as a function of kinetic energy. So the red data points are the data by AMS, and we can see that we can barely see the error bars, and this is because they have such a high statistical precision. And this is also why we can do these searches for small, spiky dark matter contributions. In blue, we have the total positron flux from our model. And then again, we have the two contributions. So at low energies, we have a dominating contribution from secondary positrons, and then at higher energies, we get the primary positrons from pulsars. And this is just a background model, so this doesn't contain any dark matter yet. And if we look at the bottom of this plot, these are the residuals. So this is data minus model divided by model. And as you can see, our model fits the data quite well to just within a few % precision. Okay, so then we take this positron flux and add a dark matter contribution to it. Could you please scroll up again? And we look at this plot here to the right. So this plot shows the dark matter contribution in the local positron flux for one dark matter annihilation at a dark matter mass of 100 GeV, and for an annihilation cross-section of 3 × 10⁻26 centimeter cubed per second for different leptonic final states. So the 4 different contributions we consider are from dark matter annihilating into tau plus 2- into mu plus mu-. Then we have a case where the dark matter first decays into a pair, or annihilates into a pair of 2 light mediators that each decay into an electron-positron pair. So we get in total 2 electron-positron pairs. That's the green line. And then we get the sharpest contribution from just direct annihilation into electron-positrons. Okay, so then we add this contribution to our background model for different dark matter masses and different annihilation cross-sections. And we compute the 95% upper confidence limit that you can see in the plot in the top right. Please, yes, scroll down, please. Yes, thank you. So this plot shows our constraints on the averaged dark matter annihilation cross-section as a function of the dark matter mass. We also added the thermal cross-section for reference. And as you can see, for taus, we get the weakest constraints, but we constrain below the thermal cross-section at about 60 GeV and lower. And for E plus E minus, we get the strongest constraints where we constrain below the thermal cross-section below about 380 GeV. And we get our strongest constraint at also for E plus E minus at 12 GeV, and for a dark matter annihilation cross-section of 6 × 10⁻29 centimeters cubed per second. Yeah, so this is our result, and this is all I wanted to say for now. So if you have any questions or comments now or later, I'm happy to discuss more. Thanks.
Thank you, Isabel. Any question?
Oh, and maybe I can just a quick comment. We will have our paper out and on arXiv in just a few weeks. So if you there will be more details. So
Great, thanks.
I have a question. How do you parameterize the pulsar contribution? I mean, do you use a continuous distribution of sources, or do you compute the expected flux from pulsars, maybe cataloged like in the ATNF catalog?
So we use a distribution. It's in the references. It's by Lorimer et al. And so this is just like a general distribution in the Milky Way. So it's not like we consider specific pulsars.
Okay, thank you.
We have this distribution. Yeah.
More questions or comments? If not, so we can switch to the next speaker, that is Paulina.
Yes, thank you. Well, my
Yes,
work
Doctor.
is based on the study of sterile neutrinos in the mu-nu SSM. It's a supersymmetric model in the context of dark matter. So if we can go down a little bit. First of all, we have to take in account the actual state of neutrino physics. We know that there are oscillations, this is transitions between different flavors, that the masses are non-zero, and we have mixing between neutrinos. And this is the table of particle data group with the actual state. So we can go down a little bit to explain the model. Our model is proposed as a natural extension with extra neutrino, right neutrino fields. We add 3 neutrino right neutrino fields. And we don't have the new problem that there is in the MSSM. Here, error parity is violated, so the phenomenology is really different from that of the MSSM and next to MSSM. Here, the superpotential, the last 3 terms are particular of this model. Maybe in the question section I can explain a little bit, but we have Majorana masses for neutrinos and Dirac-Yukawa coupling for neutrinos. Concerning the neutrino sector, a little bit down, in this model, we have a natural seesaw mechanism. The neutralinos of the MSSM mix with right-handed and left-handed neutrinos. And we have a neutralino basis of 10 particles here. And we can explain the masses of active neutrinos just diagonalizing this effective matrix with the usual unitary matrix of PMS. So, and we have these independent parameters in the neutrino sector, the BEVs, left, right, Yukawa couplings, kappa, lambda, beta, and Gaussian masses. So, stereo neutrinos, what are stereo neutrinos? Are right-handed fermions, singlets under the standard model gauge group, so they are neutral. And our purpose is to use one of the 3 right-handed neutrinos of the model in the seesaw mechanism as a stereo state. And we are interested in the Kb scale. So for that, we need to decouple one of the right-handed neutrinos from the seesaw mechanism. That is, we need to have one Yukawa coupling very, very low. And also we need to have a low kappa coupling. Kappa is the mass of the right-handed neutrinos is proportional to kappa. So if we want a Kb scale, we need a low Yukawa coupling. If you can now go up a little bit more to the first column, yes. So what we did was, first of all, a numerical analysis. We used Sphenocode generated by Sarah, a Mathematica package, for scan the parameter space needed to reproduce neutrino physics with this stereo state in the model. So as I said before, we need a low Yukawa coupling, a low kappa in order to obtain the mass scale. And also we need a low lambda coupling in order to avoid the tachyonic states that appear in the scalar and pseudoscalar sector. Because we have a very, very low Yukawa coupling to reproduce the mixing angles of neutrino physics, we need a non-diagonal Yukawa matrix. And as we can see in this table here, this is the parameter space we found that reproduces neutrino physics for a stereo neutrino between 2 keV and 90 keV. We can go down a little bit. Thank you. And this is for this parameter space, we found this value for the mixing between stereo neutrinos and active neutrinos. Secondly, we calculate the lifetime. If we can go down to the second box. For the lifetime, we have these 3 diagrams in principle, but the scalar and pseudoscalar mediating ones are suppressed with respect to the seed boson one because the Yukawa coupling and because there is a mixing between scalar and pseudoscalar with with neutrinos, and thus it's more suppressed. So the Feynman diagram corresponding to the state boson is the most relevant one, and we just calculate the decay width considering this diagram, and we obtain this value over here, which is consistent with the standard model limit plus neutrino right-handed. And we, with our values, we obtained a lifetime that is 10 to the 23 seconds, which is bigger than the age of the universe, so it's okay. And finally, if we can go a little bit down, well, here. Other important decay is from the radiative decay, because the final photon in the final state can be observed in X-ray signals. So these are the two diagrams most relevant. There are more diagrams in our model too, but they are suppressed because of the mixing or because of the couplings. And we did the calculation. We obtained this decay width, which also is consistent with the standard model limit. And we found that our results are in agreement with the constraints that there are from the mixing of the sterile neutrino, sterile active neutrino. In particular, in the case of 7Kev, we obtained this value over here, which is in perfect agreement, and it can explain the experimental evidence of the 3.5 excess. And thus, for conclude, with our results, we think the sterile neutrino is a viable dark matter candidate in this model. So that's what I wanted to tell you. Thank you.
Perfectly on time. Thanks. Any question? No questions? Comments?
Well, maybe in the color transition.
Yes, I think so. That's what I think.
Where we process all the information.
Exactly, in a more informal way. Okay, so thanks, Paulina.
Thank you.
Next speaker, Alex. Yes.
Hello, everyone. Can you hear me?
Yes, we can.
Okay, perfect. Okay, in this poster, I'm going to first. My name is Alex Len, and I'm a PhD student at the University of Trieste in Italy. And in this poster, I'm going to expose the entire search for dark matter in the cosmic ray anti-deuteron channel, especially with the GAPS experiment. So in the first left section, we have a part dedicated to the cosmic ray anti-deuteron component from dark matter annihilation or decay processes. In fact, according to some theoretical models, this antiparticle component, anti-deuteron, is predicted from to be produced from annihilation or decay processes in the galaxy. And on the other side, we have that anti-deuterons are present in the cosmic rays also as a secondary component from interaction of primary cosmic rays with interstellar medium. But we have a high energy threshold for this production of the anti-deuteron in this way, and also we have a steep energy cosmic ray energy spectrum, so that the few anti-deuterons produced have a relatively high relativistic kinetic energy. As we can see in the plot at left, we have 3 fluxes for the anti-deuterons reproduced by 3 different models of dark matter annihilation or decay. And they are compared with the magenta line, which is the astrophysical background from secondary production of anti-deuterons in cosmic rays. Okay, these fluxes are generated with the predictions not only of the dark matter models, but also for the from the expectation of the modeling of the propagation of cosmic rays in the galaxy and in the heliosphere, which is very important in the low energy range. And also in the figure, we can observe that the anti-deuterance fluxes from dark matter models are higher, at least 2 orders of magnitude higher than the fluxes from secondary production in cosmic rays below 0.25 GeV over nucleon. And so this large ratio of signal to background make this cosmic ray channel very promising. On the other side, this channel is also very challenging because it's a rare event research. No anti-deuterons have been detected yet. The best upper limit, as we can see in the figures, always on the left, was provided by BESS. But in the next years, the experiments which are AMS-02 and the future experiment GAPS will explore this channel and will provide new high sensitive limits to this measurement. About GAPS is a larger acceptance balloon-borne cosmic ray experiment. It is currently under development. Its goal is to measure low energy cosmic ray antideutrons and antiprotons, especially in energy range between 0.05 GeV and 0.25 GeV over nucleon, with a novel detection approach. And this will be performed during 3 long-duration balloon flights in Antarctica. The first one is predicted for the summer of 2022-2023. And GAPS will follow a trajectory which will be as close as possible to the lowest possible geomagnetic cutoff. This will be done in order to measure the highest possible number of low energy antiparticles. In the figure in the middle section, we have the structure of this new apparatus. It will be composed by a TOF system of 160 scintillators. These ones will be arranged into a subsystem, one outer, which is called the TOF umbrella, and the TOF at the top, and the TOF ball at the sides, and the inner tube of scintillators, which is called TOF cube. The system will provide the time information to reconstruct the particle velocity, but it will be act also as a trigger system, and will measure the of the DX deposits in the scintillators. We can go right. Okay. Inside the TOF tube, we have the tracker. The tracker is composed by 10 planes of aluminum. These are supporting planes for the lithium drifted silicon detectors. These detectors will be arranged in the 6x6 array of modules. Each modules will have 4 detectors read out by a dedicated ASIC. And then the tracker will have the major goal to measure the annihilation topology, which I will explain in a moment. Okay, the new novel detection techniques which will be performed by GAPS predict that an incoming antinucleus will enter the apparatus, slow down the ionization energy losses within the detector materials, and it will be captured by an atom of the silicon detectors. Consequently, an exotic atom in excited state will be formed. This atom will decay quickly, producing X-rays emission, and the antinucleus will be bounded more bounded states until that the antinucleus will annihilate with the nucleus, producing what is called an annihilation star, emitting secondary particles, which are pions and protons. With the measurements of the time of flight, the ionization energy losses in the sensitive materials of the apparatus, so the measurements of the precise energy of the X-rays, together with the reconstruction of the topology of the annihilation star inside the tracker, it will be possible to discriminate antideutrons from the main background of antiprotons, also to suppress all the non-antiparticle background. Thank you, that's it.
Thank you. Any question? No question for Alex? Comments? So
Maybe in Gaverton.
maybe in Gaverton that is funny. Okay, so thank you, Alex. And so next speaker is Sudipta.
Hello.
Hello, Sudipta. When you want to start.
Yeah, so I want to thank the organizer for giving me this opportunity to present his poster. So today I'm going to talk about the dark Pluto CISO in singlet doublet scenario with standard and non-standard cosmology. So can you scroll down? Okay, so let's discuss the model part. So to so here to incorporate dark matter, we are extending our standard model by SU12 doublet, and the equation 1 is present here. Is giving the Lagrangian for the BSM fields. So and the last term of equation 1 is the Euclid type interaction of the BSM field with the standard model Higgs. So after the electric symmetry breaking, Higgs will get wave. So this Euclid type interaction term will induce the mass mixing. So the neutral component of the doublet and the singlet will no longer the mass eigenstate. So you have to diagonalize the mass matrix. So after the diagonalization, you will get this Xi1 and Xi2 field, which are the mass eigenstate, and the mass eigenvalues are given in equation 2. So in this framework, one can write the mixing angle in terms of the Yukawa coupling and the mass differences, which is given by delta m. So in this picture, the dark matter talks with the standard model quarks by jet boson and also the standard model Higgs boson. So these are the mediation channels which will be responsible for the direct detections. So now we are introducing the Majorana mass term for the singlet field, which is given in the red color. Okay, so now after that we have written this Majorana mass term in Xi1 and Xi2 basis. So if we start with, we know that if we start with some Dirac mass for a field, and if we introduce very small mass for that field, then the field split it to two pseudo-Dirac field with nearly degenerate masses. So you can see this mass spectrum, which is given here. So initially you have two neutral state, Xi1 and Xi2, and in this framework the lightest one will give the dark matter. So Xi1 is the dark matter, but when you switch on the Majorana mass term, then this Xi1 is split to zeta 1 and zeta 2, and Xi2 is split to zeta 3 and zeta 4. And so you will left with 4 pseudo-Dirac state, and the lightest one, which is the zeta 1, will serve as the dark matter candidate. So in the right side we have the plot. We have plotted the mixing angle sin theta with the dark matter mass. So in the y-axis we have plotted the mixing angle, and the x-axis we have plotted the dark matter mass, and the different colors are used for different mass differences. So you can see this black dotted line in the plot, and the region below this black dotted line is the alloyed region of parameter space for the pure singlet doublet scenario when you are not writing any minor mass term. But in pseudo-Dirac case, you can see the parameter space which is large compared to the pure case. So in the pure case, the mixing angle is very much constant, but in pseudo-Dirac case, that the constant on the mixing angle is getting relaxed because of the minorness of the pseudo-Dirac dark matter. Okay, so next I will talk about the radiative generation of the neutrino mass. Okay, so here we are extending our scalar sector by the singlet fields. So in the presence of the singlet field, one can write the equotype interactions, which is written just above the Feynman diagram, which is Hij inverse I phi j. So in the presence of this equatom, one can draw the diagram. So but this is the diagram which is responsible for the neutrino mass. So you can see that the minor mass which is responsible to relax the direction bound, the same minor mass is entering to the entering to give minor mass to the neutrino. So one can calculate the mass matrix here in given in equation 4. So now I will discuss the first expanding universe. Can you scroll right? Yeah, so we know that the Big Bang nucleosynthesis happens when the universe is radiation dominated, but we still have no information about the energy budget of the universe just before the BBN. So there are several possibilities. The energy budget of the universe in the early universe can be dominated by some other species rather than radiation. And we will discuss about one such possibility. So here we are considering that the energy budget of the universe is dominated by the field eta, which has we have given the energy the behavior of the energy density with the scale factor, which is rho eta is 4 to 80 to the power minus 4 plus n. So in this scenario, one can write the expansion rate, Hubble expansion rate, which is given in equation 8. So this can you scroll? Yeah. So this expansion rate is one can written the expansion rate in terms of the expansion rate in the radiation dominated report times some factor which is given by TR to the power n. So one can see that the effect of the expansion modified cosmology can be driven by two parameters, TR and n. So TR is some reference temperature in which the energy density of the eta equals to the energy density of the radiation, and after this temperature the universe will enter to the radiation dominated universe. So now in the last section we have studied the effect of this modified cosmology in our dark matter phenomenology. So in the presence of the this modified this first expanding universe, we need larger cross section compared to the standard one to satisfy the relic density. So you can see this behavior in this figure 3. You can see the left plot of the figure 3. So over here we have plotted the relic density with the mixing angle, and where we have fixed the parameters, the mass of the dark matter and the mass differences, and also the parameter TR. So so n equal to 0 is gives us the standard picture. So as you increase the value of n, that means you are increasing the expansion rate, and that means you need larger and larger cross sections, and that is why you need larger sine theta as you increase the value of n. So we have done the same thing with the parameters, but here we have changed the mass differences from 25 to 50, and in the next in the lower panel we have done the same thing, but where we have changed the reference temperature from 0.1 GB to 1 GB. Can you scroll down? Okay, let's conclude my talk. So we have seen that in the pure singlet doublet scenario, the mixing angle is very much constant, but the pseudo-Dirac nature of the dark matter able to relax that bound. And we have seen also that the minor mass term, which is responsible for relaxing the bound on the mixing angle, it also helps us to give the minor mass to the neutrino. And also last we have discussed about the fast expanding universe, which demands larger cross sections, and which in turn also open up the mixing angle, large field of the mixing angle. Thank you.
Thank you, Sudipta. Question, comments? Probably the audience start to be tired and angry a bit, maybe. So for the time. I mean, it depends on the, yes. So any comments or questions? Okay, so if not, let's switch to the next one. That is Veronica.
Hi.
Hi.
Do you hear me well?
Yes.
Okay, perfect. So hello everyone, my name is Veronica. I'm a PhD student at University of Nova Gorica in Slovenia. Today I'll be presenting a poster about detecting and characterizing pulsar halos with Cherenkov telescope array. I will be presenting this work on behalf of my colleagues with whom we're collaborating on this project. So the Hawk Observatory has recently presented their analysis focusing on the nearby pulsars, Geminga and Monogem, which indicated that they are surrounded by spatially extended region, which is emitting multi-TeV gamma rays. Additionally, there has been some indications that the Geminga emission has also been found in the Fermi-LAT data. Further inspection raises indications that pulsar halos are likely not limited to Geminga and Monogem, but might be a feature of most pulsars, meaning that such pulsar halos possibly produce a significant fraction of the TeV diffuse emission. To explain briefly the motivation for our project, I will only mention two open questions that such work contributes to. First is the particle acceleration processes and diffusion processes that happen in our galaxy. It can bring more understanding of the origin of electrons and positrons, as some constraints can be put on the origin of the positron flux at Earth, as well as to put constraints on the values of the diffusion coefficients. The other big reason is the contribution to indirect search for dark matter, as understanding better the diffuse gamma ray emission components and having better models, therefore better estimates of the astrophysical contribution to the measured flux, can improve the knowledge of to what level the gamma ray diffuse emission could be emitted by dark matter and what would be its spectrum. So also search for extended dark subhalos is expected to be affected by these source observations, and this can help us put further constraints on dark matter interactions and its particle physics properties. So these TeV halo pulsar halos that Hawk identified might be numerous and bright enough to constitute a large fraction of the sources that will be observed with the Cherenkov telescope array, especially in the context of the Galactic Plane Survey, which is one of the key science projects of CTA. In this study, we examined the prospects offered by CTA for the detection and characterization of such objects. First, we examine the prospects for detection of simple Gaussian extended sources, and then we move the same analysis to a particular physical model of the source. I believe most of you are familiar with CTA to some extent, but just to provide a short description, CTA is the next generation ground-based observatory for gamma ray astronomy at very high energies. It will be detecting gamma rays in the range between 20 GeVs and 300 TeVs. It will consist of an array of imaging atmospheric Cherenkov telescopes at two different locations. One will be at the southern and another at the northern hemisphere, which will enable CTA to observe the whole sky. It is aiming to improve the sensitivity of the current telescopes, such as HESS, MAGIC, and VERITAS, by an order of magnitude at TeV energies, as well as to improve their angular resolution, better the field of view, and energy coverage, which will then result in increased ability to image these extended sources. Preliminary population studies have shown that CTA could detect roughly half of such TeV halo sources and even resolve the shape of their profile for a significant number of such sources. In our calculation, we focused on using the proposed key science project plan of CTA called the Galactic Plane Survey, which proposes to carry out a survey of a full galactic plane using both the southern and northern CTA observatories. The observations are planned during dark time under good weather conditions and at zenith angles that are less than 45 degrees. And for the observations, they propose a double row pointing strategy with a pointing separation distance of 3 degrees. For some of the most promising regions, such as, for example, the intergalactic region, it has been proposed to receive higher observation time and with that deeper exposure than other regions. And this can also be seen in this figure 1 that shows the simulated map of expected cosmic ray background exposure of the galactic plane survey that will be reached during these proposed observations. So we see that there is a galactic plane, there is a region in the middle going between -60 and 60 degrees in latitude, longitude that will receive higher observation time than others, and with that higher exposure. So our group designed our calculations in a way that we chose different positions in the sky that were covered by this proposed galactic plane survey and examined the sensitivity to a particular source that is placed at a particular position. So these preliminary sensitivity curves are shown in figures 2 and 3. So we can move first to figure 2. We started by taking into consideration the simplest possible model of a source, such as just an extended Gaussian source with different extensions. In this case, we use extensions 0.2, 0.5, and 2 degrees, and we placed it at 2 distinct positions in the sky. In my plot here, I show, I consider position in the galactic center and the position at galactic latitude of 0 degrees and longitude of -10 degrees. So the plot shows that sensitivity curves obtained by considering only the galactic plane survey cosmic ray background. We have calculated same sensitivities also considering the interstellar emission, but these had little effect on the sensitivity values. So I have not included it in the figures here. And this analysis is specifically targeted to assess the sensitivity to extended sources. And in this context, it shows that the more extended sources reach worse sensitivity than less extended ones, which is because more extended sources are harder to distinguish from the background. So we also see here that there is a little but noticeable difference between the 2 positions in the sky, which is due to a small difference in the exposure of the galactic plane survey at these 2 chosen locations. Moving on to figure 3. In the next step, then we used a physical model for TeV halos. So these models are obtained by solving the diffusion loss equation for pairs injected from the pulsar and its nebula, and then diffusing away in a 2-zone model in which diffusion is low within some distance, in our case 50 parsecs, and some distance to the source, and then typical for the interstellar medium beyond that distance. The values of some model parameters, such as h of the pulsar, its spin down power, timescale, and the diffusion coefficient normalization, are given in a footnote A, while this characteristic distance that we use is, as I mentioned, 50 parsec. So just to stress here that these values are for some very generic pulsar halo models. Again, only considering the cosmic ray background, we obtained this sensitivity shown in figure 3. This time just for one chosen position at the sky at -10, 0 degrees of longitude and latitude. The plots shows a sensitivity for 2 physical sources positioned at 2 different distances from Earth. One is 1 kiloparsec and another is 3 kiloparsecs away. At this point, we also added different levels of systematic uncertainty in our sensitivity calculations. And for the implementation of systematics, we followed the CTA consortium publication that is also cited in the references. From the plots, we see that the physically modeled sources can be detected over the whole CTA energy band, and also accounting for the systematics at 10% level does not significantly affect the detectability of the source, although there is no fully established model of the benchmark on the systematics that should be used in this case yet. Another comment is that these outliers that you can see at higher energies are due to a numerical convergence issue in our code. So we're still in the process of resolving this. So to conclude, given CTA's expected performance, this preliminary study shows that CTA promises good sensitivity to detecting pulsar halo sources over the whole CTA energy band. And with that represents a promising tool to significantly contribute to answering some open questions in the nature of pulsar halos. On the next step in our analysis, we'll perform a more detailed population study by considering the pulsars in the ATNF catalog and then assigning them some pulsar halos and perform the sensitivity limits on these pulsars, identifying how many of them could be visible to CTA and also characterizing whether or not their profiles could be resolved and to what extent. So this was all from my side. Thank you very much.
Okay, thank you. Veronica, any question? No questions? Comments? Suggestions? Okay, so in Gathertown also, I suppose. So we can move to the last speaker of this poster section, that is Mateus.
Hi, yes. I believe I used the same template as Veronica. So, yeah. Well, hello, everyone. My name is Mateus. I study in University of São Paulo in Brazil. And today I'm going to briefly talk about my master's project, which I started this year. So it's in the early stages, so I don't have much results to present. But I want to give a little bit of context about my work. So you may know that since the formation of the first stars and galaxies in the universe, the light emitted by them permeates the voids and is redshifted by cosmological expansion. And you also have the starlight absorbed by dust and reprocessed in longer wavelengths. So all this light from the ultraviolet to the far infrared is what we call the extragalactic background light, which we heard a little bit yesterday, and we surely learn more about it tomorrow. So it's very important to quantify the EBL, the extragalactic background light, because it can tell us about the star formation and structure formation histories of the universe. However, it's actually very hard to directly measure it because there's a lot of foreground contamination from galactic sources and also from the solar system itself. So gamma rays can help us exactly to probe the EBL. So what happens is that gamma rays, high energy and very high energy photons, can interact with those low energy photons from the EBL and produce electropositron pairs. So this pair production represents an effective attenuation of the flux emitted by the sources. And the way we quantify this attenuation is from the optical depth. I'm sorry, I don't have the mathematical expression here, but the optical depth is essentially an integral over the numerical density of the EBL. So more EBL photons, more attenuation is expected, times the cross-section of photon-photon interaction. And it's an integral over the redshift from the source to the observer. So for instance, in figure 1a, which it should be 1, but it's only A in the poster, and there's an example of a spectra of a blazar, so an AGN with the jet pointed towards us. It's actually a simulated observation, it's not real data, but we can see in the dashed black line the intrinsic spectra as modeled as a power law, a simple power law, and the red line is the model with EBL attenuation. So what EBL does, the attenuation of gamma ray photons gives an exponential attenuation essentially to the flux. But the problem is that we frequently don't know in real observations how it is the true EBL spectrum and the true intrinsic spectrum of sources. So one way to deal with both kinds of uncertainties in our analysis is to simultaneously fit the observed data with an EBL model and also an intrinsic flux model for the source. So my work is dealing with these general problems, that to extract parameters of the EBL and from observed sources, but in the context of this Cherenkov telescope array, the CTA. So of course, CTAs will be very important to collect very high energy data at dozens of TeV, which is a range of gamma ray energies that can interact with the far infrared region of the EBL. So it's a region dominated by dust emission. So it's actually a new region that we can probe with CTA. And my group, the research group I work with, it's simulating observations of lasers using C-tools to give a more realistic perspective on what CTA will, the data that CTA will collect in their extragalactic survey. So we hope to, with this simulated sample, to have a better understanding of the properties that EBL, what properties of the EBL we can constrain using our models and this data, right? So we are currently using Fink's 2010 EBL model. It's a model in figure 1b, as it's just the example. It's a model that considers the EBL as a sum of a stellar component and 3 types of dust. So each type of dust has a proportion factor, a fraction, and we can fit this proportion fraction, changing the contribution of each type of dust grain. So this has the effect of changing the attenuation of very high energy photons, and the proportion of it. So in figure 2, I present, this can lower, yes. I present the a result of MCMC simulation, Markov chain Monte Carlo simulation, in which you fit this fraction in 2 cases. One, we combine 2 sources, 2 simulated sources, and in the second row, 5 simulated sources. So we can see the expected result, but just preliminary, that when you combine many sources, when you combine many observations, we have reduced uncertainties, and we can constrain even better the EBL properties. So the things that the perspective is to study all these cases, how many sources we can combine, what kind of constraints we can achieve in different EBL models and in different intrinsic spectrum models too. So we can study the impact of CTA on these types of constraints. So this is just a brief overview of my work. If you have any questions about the methodology or anything, you can write me an email or we talk later. Anyway, so thank you so much for your attention.
Thank you, Mateus. We are also perfectly on time. Question, comments? Apparently not. Last chance.
Okay, I can go.
Okay.
I have a question, Mateus. By the way, very nice stuff. Of course, I am very much interested also on the EBL. So yeah, very nice work. I have a question about the EBL models that you are considering now and the ones that you are going to consider in the future. I mean, I don't know if you maybe thought about that, or because I as far as I understand, the state-of-the-art models, EBL models, are not so different from each other, right? So is there any way to be more sensitive in your work to these models?
Yes, we are working with mostly this Fink EBL model because it has a direct physical interpretation. So we know what is the contribution of dust components and stellar components, but it's also, there's also a Domingues model, which Domingues will present, right? The lecture on Friday, and his model is very utilized in the literature. And although it's very similar in in the overall shape, there are some differences in the, especially in the infrared region. So the idea, for instance, is, since we are simulating the observations, is to change the real, the true EBL spectrum, the true attenuation. So for instance, if we simulate sources that are absorbed, and the flux is absorbed by Domingues' model, we can try to study how using Fink's model we can reproduce or not the attenuation that Domingues predicts. So it's to study those types of things. The possibility to constrain different EBL models from. Sorry, I saw a question here. To constrain different EBL models using different parameters. It's kind of something like that. So I don't know if I.
Yes, I understand. Thank you. Thank you so much.
Okay. I have a question from Lorenzo. Can you explain the expected signatures of dark matter from EBL? Probably yes. I don't work with dark matter, but CTA, I believe there's a lot of work in this direction from. Well, I don't know if from the EBL exactly, right? From gamma ray attenuation and the prospect of axion-like particles interacting with gamma rays, but I don't know exactly from EBL. It's a good question, actually.
Okay, more questions? If not, I'm going to close the stream now. Okay. So thank you again to all the poster contribution, and see you in the afternoon section.